Welcome back, everybody. We're continuing with our additions to alkenes. We're going to do regioselective, non-stereospecific additions. We did water additions, hydrations, and we're just switching the reagent from water to alcohol. And you might think that's a major switch, but for molecules, it's really not a big switch, because alcohols, let's say like methanol, have got just a carbon in place of a hydrogen. That's the only difference. So hydrogen here for water is just methanol has got just a carbon. If it's any other alcohol, you just have an R group, and all of them would do the same thing. I kept the scheme from the hydration just to show you how very, very similar the mechanism is for hydration and for the alcohol addition. In fact, it's also very similar for the HX addition, because they're all non-stereospecific Markovnikov regioselective reactions. Same bucket, same mechanism in this case. All right, let's start. So we had earlier water and H2SO4. Here you have catalytic H2SO4, which is like maybe like a 0.1 equivalent of H2SO4 in methanol. And that is going to pick up a proton from the H2SO4 and give you a CH3O+. So initial step, because you have an excess of methanol, it's going to be protonated. You have very little sulfuric acid here. And so this is something that happens a lot in carbohydrate chemistry as well. So here is a methanol that is acidic. So you have CH3OH+, and you have a proton here that is going to be acidic, very acidic, right? pKa maybe less than 2 now, minus 2. All right, so this is going to grab that proton, and you would get a carbocation on A. That's right, not B, because that's secondary. Same mechanism, guys. So you have a hydrogen here and a carbocation. Now that is going to be attacked by methanol. Earlier we attacked it with water, HOH. Now it's just CH3OH. So as long as you have one hydrogen here, it would work, because you know that in the next step, you would have to remove that hydrogen for it to be neutral. So now you lost your lone pair electrons, and therefore you have a positive charge. And now that you have a hydrogen, hydrogens can just hop on and hop off. It's like always on a tour bus, okay? So a hop on, hop off bus. So here your methanol just decides to hop off on another methanol. So there you go. So you would get this. Take off the proton, giving you a neutral methanol. Again, this is a flat sp2 carbocation, which can be attacked from above and below in equal amounts. So I'm going to put a squiggly line to show that. It can be above and below. So your product will have an OCH3 on a wedge and an OCH3 on a dash. So it's going to be a raceme because it is non-stereospecific. Therefore, both are equally likely to form in a raceme. Now, we did a rearrangement here, and we said that was the major product. Again, same thing as before, the secondary carbocation. If we can rearrange to a tertiary, why not? It's going to do it. So it rearranges and gives you the most stable carbocation, which then again is attacked by the methanol above and below. It really doesn't matter because it's achiral, and you would get an OCH3 that is now positive because it lost a lone pair. And then there's one little hop now to go to your product by deprotonating that methanol. So you can see when you have an alcohol, the mechanism is almost identical to that of a water molecule. So here is your OCH3, which is an ether product. So your ether is the major product here. And it's the same here. You got two ethers, racemic R and S. All right, now that we've kind of figured out that methanol addition is almost identical in mechanism to water addition, let's do some fun stuff here. Here's a four-membered ring, and look what happened in your product. It kind of expanded, it grew. How did it do that? Let's look at it. Well, I put ROH, it could be any alcohol. I just want to tell you that it doesn't matter what the R group is, the mechanism's the same. This is going to be your major product for sure. All right, let's do it. ROH with catalytic H2SO4, same deal as before. And just for simplicity, let's make the R group an ethyl group here. So it's ETOH or CH3CH2OH. Grabbing a proton from sulfuric acid, because this is catalytic, so pretty much all of it is going to be grabbed by the lone pairs to give a CH3CH2OH plus. So this is a protonated alcohol, and that's very acidic. So you'll have a protonated alcohol, it's positive, and it's waiting to unload those protons onto anything that would have it. So the alkene, double bonds jump out and catch that proton that on the ethanol. Now, it could have got this or this. So it's going to have a protonated alkene. And where do you think it's going to go? If I label this A and B, Markovnikov. Well, Markovnikov did say that hydrogens are going to end up on the carbon, that has more hydrogens. So you are going to have 2 hydrogens here versus 1 hydrogen here. It's a no-brainer. It's going to go over here. Now that means you're going to have a gaping hole here, which is going to be just inviting any and every nucleophile out there to come get it. Well, you could attack that, but it's secondary, not too hot. And so you could move this hydrogen over and do a hydride shift and get a tertiary. I mean, that's pretty good, but that's still going to give you a 4-membered ring. Is that going to be okay? That's not too hot. We want a tertiary. How can we do a tertiary? Can we move this over and get a tertiary? Let's try it out. Let's see if that works. So let's take these 2 electrons and roll up a house and creep into this empty orbital. Let's see if that does it. So here we are going to then have this break up and form a carbocation right here on this carbon. That's attached to this methyl group. And I'm just going to draw it out just to show that the hydrogen went over here. All right, so now since we rolled our house up and moved over here, this carbon here is going to be electron deficient because we just pulled electrons out of here. This only got 1 hydrogen and 2 carbons. So this becomes positive. However, this is also secondary. Uh-oh, well, not a good thing. After all of that, I'm still secondary. What's the point? Well, you could do a tertiary right here because there are 3 carbons. However, there's a hydrogen here. So now what you do is you can roll up your house and move over here into this empty house to get a tertiary right there. So that's how you get a tertiary. You do like a double rearrangement. So now you have 2 hydrogens here, but no hydrogen on this carbon. This is your empty gaping hole, but it's kind of happy because it's on a tertiary. Yippee! It's pretty happy. This guy's donating electrons, this guy's donating electrons, this guy's donating electrons. It's rolling it up, sucking all that attention. It's quite happy there. And it's really a flat carbocation. So if I write it out like this, it's going to look like this. You're going to have a positive right here, and you will have a methyl on the side. Now that we have a carbocation here, what are the possibilities for this molecule? Can it rearrange further? It's not going to do that. It's already in its prime tertiary carbocation stage. So it's going to stay right there. Besides, 5-membered rings are way better than 4-membered rings. Remember angle strain? So you relieved yourself of angle strain, and so it's never going to go back. So from this point after the rearrangement happens, it's pretty much going towards your product. All right. Now that you have this is the exact same as this. You're going to have an ethanol pouring into this because you need a nucleophile to attack. Ethanol comes in and it can attack above or below. Does it matter? No, it's achiral. So therefore, it's going to attack above and below. You just can't tell which one just because the product's identical. And I'm going to write this as a CH3. And here you're going to have your oxygen with a hydrogen still sticking onto it. And then you'll have your ethyl group. Well, do you want to leave it like that? No, we have a nice workup process, which means you're just washing it out. And here you'll have CH3, CH2, OH. Do the job of deprotonating it so you can have a very nice and neutral ether group there cozying up with that alkyl group. So here is your OET. This is the same thing that I have written here as an OR group. So here is your methyl OR. This is your major. Now, what is your minor? Minor could be attack of this carbocation with a ethanol. It could be attack of this hydrogen moving over and giving you a tertiary. So there may be other minor products, but because you have a ring expansion to a more stable 5-membered ring, the conformation here is a lot more stable than this. This is then going to be energetically favored. So therefore, most of your reaction over time would end up over here. Now, whenever you have these proton reactions, a lot of these are reversible. So it's a good idea to put reversible arrows, because the protons just jump on and off and give you more and more reactions. So all of these are reversible reactions. Just want to let you know. But sometimes when you have a ring expansion like this to a 5-membered ring, going back to a 4-membered is very unlikely energetically. All right. You can have hydride shift. You can have methyl shift. You could have alkyl shift. You could have ring expansion. All